Nenomatica, where mathematics meets YouTube excellence. Welcome to this mathematics video. Today we'll solve a system of equations with variables a, b, and c. Let's take a look at the system we need to solve. Let's recall a helpful mathematical property. For any positive real numbers x, if x plus 1 over x is greater than or equal to 2, then this sum is minimized when x equals 1, giving us exactly 2. Looking at our system of equations, we can make an important observation. We have expressions of the form a plus 1 over a, b plus 1 over b, and c plus 1 over c. Based on our property, each of these expressions is greater than or equal to 2. Let's analyze the first equation. We have the product of two expressions, a plus 1 over a multiplied by b plus 1 over b equals 3. Since each of these expressions is greater than or equal to 2, their product must be greater than or equal to 4. But this leads to a contradiction. Our first equation states that this product equals 3, but we've just shown that it must be at least 4. So we have 3 greater than or equal to 4, which is clearly false. From this contradiction, we can conclude that the system has no solution. The constraints of our system force the product to be 3, but the mathematical property we used forces the product to be at least 4. These contradictory requirements mean there are no values of a, b, and c that can simultaneously satisfy all equations in our system. In this video, we'll be solving a system of equations. Let's begin by looking at the system we need to solve. Here's our system of equations. We have two equations, x equals 2y squared over 1 plus y squared, and y equals 2x squared over 1 plus x squared. Let's analyze what happens when we compare the values of x and y in this system. We can note some important relationships from the formulas. Looking at our relationships, we have both y is less than or equal to x, and x is less than or equal to y. The only way both these inequalities can be satisfied is if x equals y. Now, we substitute x equals y into one of our original equations. Let's substitute it into the first equation. We get x equals 2y squared over 1 plus y squared. And since x equals y, we can write y equals 2y squared over 1 plus y squared. We can also substitute x equals y into the second equation. This gives us y equals 2x squared over 1 plus x squared, which becomes y equals 2y squared over 1 plus y squared since x equals y. Now, let's solve the equation y equals 2y squared over 1 plus y squared. First, we multiply both sides by 1 plus y squared to get y times 1 plus y squared equals 2y squared. Expanding the left side, we get y plus y cubed equals 2y squared. Let's rearrange all terms to one side to get a standard form polynomial equation. We get y cubed minus 2 y squared plus y equals 0. We can factor out y from all terms to get y times y squared minus 2 y plus 1 equals 0. Looking at the expression inside the parentheses, we can recognize that y squared minus 2y plus 1 is a perfect square trinomial. It can be written as y minus 1 squared. Now we can solve the equation. Since we have a product equal to 0, either y equals 0 or y minus 1 squared equals 0. From the second equation, y minus 1 squared equals 0 implies that y equals 1. So we have two solutions, either y equals 0 or y equals 1. And since x equals y, we also have x equals 0 or x equals 1. Let's verify our solutions by substituting them back into the original system. For the first solution, x equals 0 and y equals 0, let's check the first equation. We get 0 equals 2 times 0 squared over 1 plus 0 squared, which is 0 equals 0. For the second equation, we get 0 equals 2 times 0 squared over 1 plus 0 squared, which is also 0 equals 0. So, the first solution is verified. Now, let's verify the second solution, x equals 1 and y equals 1. For the first equation, we have 1 equals 2 times 1 squared over 1 plus 1 squared, which gives us 1 equals 2 over 2, or 1 equals 1. For the second equation, we get 1 equals 2 times 1 squared over 1 plus 1 squared, which is also 1 equals 1. Therefore, the second solution is also verified. We need to prove that for real numbers x and y, x squared plus y squared is greater than or equal to 2xy. For our first step, we'll move all terms to one side of the inequality. This gives us x squared plus y squared minus 2x. Y is greater than or equal to 0. For our second step, we'll recognize that this expression is actually a perfect square. We can factor it as open parenthesis x minus y close parenthesis squared is greater than or equal to 0. For our final step, we'll use the fact that any squared real number is always non-negative. Since open parenthesis x minus y close parenthesis squared is always greater than or equal to 0, this means our original inequality x squared plus y squared is greater than or equal to 2x. Y is always true for any real numbers x and y. Now, let's move on to our second example. We need to prove that for real numbers x and y, x over y plus y over x is greater than or equal to 2. For our first step, we'll move all terms to one side of the inequality. This gives us x over y plus y over x minus 2 is greater than or equal to 0. For our second step, we'll rewrite this in a form that we can manipulate further. We can express this using the square of the difference of square roots. This gives us open parenthesis square root of x over y minus square root of y over x close parenthesis squared is greater than or equal to 0. For our final step, we'll use the fact that any squared real number is always non-negative. Since open parenthesis square root of x over y minus square root of y over x close parenthesis squared is always greater than or equal to 0, this means our original inequality x over y plus y over x is greater than or equal to 2 is always true for any real numbers x and y. For real numbers x and y, prove that x plus y times 1 over x plus 1 over y is greater than or equal to 4. Let's solve this step by step. First, we'll expand the left side of the inequality by multiplying the two expressions. We get x times 1 over x plus x times 1 over y plus y times 1 over x plus y times 1 over y. Now, let's simplify the expressions. When we multiply x times 1 over x, we get 1. Similarly, when we multiply y times 1 over y, we also get 1. For the remaining terms, we get x over y plus y over x. So our inequality becomes 1 plus x over y plus y over x plus 1, which simplifies to 2 plus x over y plus y over x is greater than or equal to 4. Let's subtract 2 from both sides to get a cleaner form of the inequality. We get x over y plus y over x is greater than or equal to 2. Now, we need to show that x over y plus y over x is greater than or equal to 2. This is where we can use the AMGM inequality, which states that the arithmetic mean of positive numbers is greater than or equal to their geometric mean. Using the AMGM inequality, we know that the arithmetic mean of x over y and y over x is greater than or equal to their geometric mean. That is, x over y plus y over x divided by 2 is greater than or equal to the square root of x over y times y over x. Let's simplify the right side. X over y times y over x is equal to x times y divided by y times x, which equals 1. So the square root of this is also 1. Now we can multiply both sides by 2 to get that x over y plus y over x is greater than or equal to 2. This shows that our original inequality is always true. That is, x plus y times 1 over x plus 1 over y is always greater than or equal to 4 for all real numbers x and y. Now, let's look at our second example. Prove that for real numbers x and y, x squared plus y squared minus x, y is greater than or equal to 0. Let's solve this inequality. First, let's multiply both sides of the inequality by 2 to make our calculations easier. We get 2x squared plus 2, y squared minus 2x. Y is greater than or equal to 0. Now, we'll split this expression into two parts. We can rewrite this as the sum of x squared plus y squared and x squared plus y squared minus 2xy. This gives us x squared plus y squared plus x squared plus y squared minus 2xy is greater than or equal to 0. Notice that the second term, x squared plus y squared minus 2xy, is actually the perfect square of x minus y. Using the formula for the square of a binomial difference, we can rewrite this as x squared plus y squared plus x minus y squared is greater than or equal to 0. Now, we have a sum of three perfect squares, x squared, y squared, and x minus y squared. Since squares of real numbers are always non-negative, The sum of these three terms must always be greater than or equal to 0. This proves our inequality. We need to prove that for any real numbers x, y, and z, the following inequality holds true. X squared plus y squared plus z squared is greater than or equal to xy plus yz plus cx. Let's begin our proof. The first step is to rearrange the inequality by subtracting the right side from both sides. This gives us x squared plus y squared plus z squared minus xy minus yz minus cx is greater than or equal to 0. Next, let's multiply all terms by 2 to make our work easier. This gives us 2x squared plus 2y squared plus 2z squared minus 2x, y minus 2, yz minus 2zx is greater than or equal to 0. Now for the key step. We'll rearrange the terms to form perfect squares. This gives us the sum of three terms x squared minus 2x, y plus y squared minus 2yz plus z squared minus 2zx plus x squared, all greater than or equal to 0. Let's recognize these as perfect squares. The first term is x minus y squared, the second term is y minus z squared, and the third term is z minus x squared. So we have x minus y squared plus y minus z squared plus z minus x squared is greater than or equal to 0. Since the sum of squares is always non-negative, our inequality is always true. Therefore, x squared plus y squared plus z squared is always greater than or equal to xy plus yz plus cx. The equality holds when x equals y equals z, making all squared differences 0. Now, let's move on to our second example. We need to prove that for any real numbers x and y, the following inequality holds true. X squared plus y times the quantity x squared plus 1 is greater than or equal to 4xy. Let's begin our proof. First, we'll rearrange the inequality by subtracting the right side from both sides. This gives us x squared plus y yx squared plus y minus 4xy is greater than or equal to 0. Let's expand and rearrange the terms. Simplifying, we get x squared plus y yx squared plus y minus 4xy is greater than or equal to 0. Combining like terms, we get x squared minus 2x, y plus y squared plus yx squared plus y minus 2xy is greater than or equal to 0. Now, we recognize that the first term is a perfect square. So our inequality becomes x minus y squared plus yx squared plus y minus 2xy is greater than or equal to 0. Next, let's factor out y from the remaining terms. This gives us x minus y squared plus y times x squared minus 2x plus 1 is greater than or equal to 0. Looking at the expression inside the parentheses, we can recognize another perfect square. So our inequality becomes x minus y squared plus y times the quantity x minus 1 squared is greater than or equal to 0. Since both terms are squares, and y is assumed to be positive, the entire expression is always greater than or equal to 0. Therefore, our original inequality, x squared plus y times the quantity x squared plus 1 is always greater than or equal to 4xy. The equality holds when both x minus y and x minus 1 are 0, which happens when x equals y equals 1. Let's summarize what we've learned today. We proved two important inequalities. First, that x squared plus y squared plus z squared is greater than or equal to xy plus yz plus cx. Second, that x squared plus y times the quantity x squared plus 1 is greater than or equal to 4xy. In both cases, we used algebraic manipulation, particularly the technique of completing the square, to express our inequalities as sums of perfect squares, which are always non-negative. This approach is powerful for proving many mathematical inequalities. We need to prove the following inequality: x squared, y plus y squared z plus z squared, x plus xy squared plus yz squared plus cx squared is greater than or equal to 6xyz. Our first step is to group the terms strategically. We'll organize them into 3 groups, each containing 2 related terms. In the next step, we'll factor out common terms from each group to create a more recognizable pattern. Notice how we factor out y from the first group, z from the second group, and x from the third group. Now, we can recognize that each parenthesis contains a perfect square difference. For example, x squared plus z squared minus 2x z equals the square of x minus c. And now we can see that our expression is a sum of perfect squares multiplied by positive numbers, assuming x, y, and z are positive. Since squares are always non-negative, and we're multiplying them by positive values, the entire sum must be greater than or equal to 0. Therefore, the original inequality is always true. The left side of our original inequality is always greater than or equal to 6xyz. Now, let's move to our second example. We need to prove that x cubed plus y cubed is greater than or equal to x squared, y plus y squared x, given that x is less than or equal to y. Let's begin by rearranging the inequality to get a more workable form. We'll move all terms to the left side. Now, we'll factor out common terms. Notice how we factor out x squared from the first two terms and y squared from the last two terms. Let's further simplify this expression by combining the terms. Notice that the second term has y minus x, which is the negative of x minus y from the first term. Now, we can factor out the common term x minus y. We can further simplify the second factor, x squared minus y squared, which is a difference of squares. It equals x minus y times x plus y. Now, let's analyze this inequality using our given constraint that x is less than or equal to y. First, we know that x minus y is less than or equal to 0 because x is less than or equal to y. This means that the first two factors, both equal to x minus y, are both less than or equal to 0. Since we have the product of two non-positive numbers, this part of the expression is non-negative. And the third factor, x plus y, is positive assuming x and y are positive. So the entire expression is non-negative. Therefore, the original inequality x cubed plus y cubed is greater than or equal to x squared, y plus y squared x is always true when x is less than or equal to y. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. Nenomatica, where mathematics meets YouTube excellence.